it is with no common pleasure that I take up my pen to dedicate these volumes to you. They are the result of trains of thought which have often been the subject of our conversation, and of which the origin goes back to the period of our early companionship at the university. And if I had ever wavered in my purpose of combining such reflections and researches into a whole, I should have derived a renewed impulse and increased animation from your delightful discourse on a kindred subject. For I could not have read it without finding this portion of philosophy invested with a fresh charm. And though I might be well aware that I could not aspire to that large share of popularity which your work so justly gained, I should still have reflected that something was due to the subject itself, and should have hoped that my own aim was so far similar to yours that the present work might have a chance of exciting an interest in some of your readers. That it will interest you, I do not at all hesitate to believe. If you were now in England, I should stop here. But when a friend is removed for years to a far distant land, we seem to acquire a right to speak openly of his good qualities. I cannot, therefore, prevail upon myself to lay down my pen without alluding to the affectionate admiration of your moral and social, as well as intellectual excellencies, which springs up in the hearts of your friends whenever you are thought of. They are much delighted to look upon the halo of deserved fame which plays round your head, but still more, to recollect. 6, as one of them said, that your head is far from being the best part about you. May your sojourn in the southern hemisphere be as happy and successful as its object is noble and worthy of you, and may your return home be speedy and prosperous as soon as your purpose is attained. Ever, my dear Herschel, yours. W. Whewell, March 22, 1837. P.S. So I wrote nearly 10 years ago, when you were at the Cape of Good Hope, employed in your great task of making a complete standard survey of the nebulae and double stars visible to man. Now that you are, as I trust, in a few weeks about to put the crowning stone upon your edifice by the publication of your observations in the southern hemisphere, I cannot refrain from congratulating you upon having had your life ennobled by the conception and happy execution of so great a design, and once more offering you my wishes that you may long enjoy the glory you have so well won. W. Trinity College, Nov. 22, 1846. 7. Preface to the third edition. In the prefaces to the previous editions of this work, several remarks were made which it is not necessary now to repeat to the same extent. That a history of the sciences, executed as this is, has some value in the eyes of the public, is sufficiently proved by the circulation which it has obtained. I am still able to say that I have seen no objection urged against the plan of the work, and scarcely any against the details. The attempt to throw the history of each science into epochs, at which some great and cardinal discovery was made, and to arrange the subordinate events of each history as belonging to the preludes and the sequels of such epochs, appears to be assented to, as conveniently and fairly exhibiting the progress of scientific truth. Such a view being assumed, as it was a constant light and guide to the writer in his task, so will it also, I think, make the view of the reader far more clear and comprehensive than it could otherwise be. With regard to the manner in which this plan has been carried into effect with reference to particular writers and their researches, as I have said, I have seen scarcely any objection made. I was aware, as I stated at the outset, of the difficulty and delicacy of the office which I had undertaken, but I had various considerations to encourage me to go through it, and I had a trust, which I, 8, have as yet seen nothing to disturb, that I should be able to speak impartially of the great scientific men of all ages, even of our own. I have already said in the introduction that the work aimed at being, not merely a narration of the facts in the history of science, but a basis for the philosophy of science. It seemed to me that our study of the modes of discovering truth ought to be based upon a survey of the truths which have been discovered. This maxim, so stated, seems sufficiently self-evident, yet it has, even up to the present time, been very rarely acted on. Those who discourse concerning the nature of truth and the mode of its discovery still commonly make for themselves examples of truths, which for the most part are utterly frivolous and unsubstantial, as in most treatises on logic. Or else they dig up, over and over, the narrow and special field of mathematical truth, which certainly cannot, of itself, exemplify the general mode by which man has attained to the vast body of certain truth which he now possesses. Yet it must not be denied that the ideas which form the basis of mathematical truth are concerned in the formation of scientific truth in general. And discussions concerning these ideas are by no means necessarily barren of advantage. But it must be borne in mind that, besides these ideas, there are also others, which no less lie at the root of scientific truth, and concerning which there have been, at various periods, discussions which have had an important bearing on the progress of scientific truth, such as discussions concerning the nature and necessary attributes of matter, of force, of atoms, of mediums, of kinds, of organization. The controversies which have taken place concerning these have an important place in the history of natural science in 9, its most extended sense. Yet it appeared convenient to carry on the history of science, so far as it depends on observation, in a line separate from these discussions concerning ideas. The account of these discussions and the consequent controversies, therefore, though it be thoroughly historical, and, as appears to me, a very curious and interesting history, is reserved for the other work, the philosophy of the Inductive Sciences. Such a history has, in truth, its natural place in the philosophy of science, for the philosophy of science at the present day must contain the result and summing up of all the truth which has been disentangled from error and confusion during these past controversies. I have made a few additions to the present edition, partly with a view of bringing up the history, at least of some of the sciences, to the present time so far as those larger features of the history of science are concerned, with which alone I have here to deal, and partly also, especially in the first volume, in order to rectify and enlarge some of the earlier portions of the history. Several works which have recently appeared suggested reconsideration of various points, and I hoped that my readers might be interested in the reflections so suggested. I will add a few sentences from the preface to the first edition. As will easily be supposed, I have borrowed largely from other writers, both of the histories of special sciences and of philosophy in general. I have done this without scruple, since the novelty of my work was intended to consist, not in its superiority as a collection of facts, but in the point of view in which the facts were placed. I have, however, in all cases, given references to my authorities, and there are very few instances in which I have not verified the references of previous historians and studied the original authors. According to the plan which I have pursued, the history of each science forms a whole in itself, divided into distinct but connected members by the epochs of its successive advances. If I have satisfied the competent judges in each science by my selection of such epochs, the scheme of the work must be of permanent value, however imperfect may be the execution of any of its portions. Note 1\p. Among these, I may mention as works to which I have peculiar obligations, Tenemann's Geschichte der Philosophie, de Girando's Histoire comparée des systèmes de philosophie, Montacle's Histoire des mathématiques, with Delaland's continuation of it, Delamber's Astronomie ancienne, Astronomie du Moyen Age, Astronomie moderne, and Astronomie du XVIIIe siècle, Bailey's Histoire d'Astronomie ancienne, and Histoire d'Astronomie moderne. Voiron's Histoire d'Astronomie, published as a continuation of Bailey, Fischer's Geschichte der Physik, G. Mellon's Geschichte der Chemie, Thomson's History of Chemistry, Sprengel's History of Medicine, his History of Botany, and in all branches of natural history and physiology, Cuvier's works, in their historical as in all other portions, most admirable and instructive. With all these grounds of hope, it is still impossible not to see that such an undertaking is, in no small degree, arduous and its event obscure. But all who venture upon such tasks must gather trust and encouragement from reflections like those by which their great foreigner prepared himself for his endeavors, by recollecting that they are aiming to advance the best interests and privileges of man, and that they may expect all the best and wisest of men to join them in their aspirations, and to aid them in their labors. Concerning ourselves we speak not, but as touching the matter which we have in hand, this we ask, that men deem it not to be the setting up of an opinion, but the performing of a work, and that they receive this as a certainty that we are not laying the foundations of any sect or doctrine, but of the profit and dignity of mankind. Furthermore, 11, that being well disposed to what shall advantage themselves, and putting off factions and prejudices, they take common counsel with us, to the end that being by these our aids and appliances freed and defended from wanderings and impediments, they may lend their hands also to the labors which remain to be performed. And yet, further, that they be of good hope, neither feign and imagine to themselves this our reform as something of infinite dimension and beyond the grasp of mortal man, when in truth it is of infinite error, the end and true limit, and is by no means unmindful of the condition of mortality and humanity, not confiding that such a thing can be carried to its perfect close in the space of one single day, but assigning it as a task to a succession of generations. Bacon Instauratio Magna Pref. Ad fin. If there be any man who has it at heart, not merely to take his stand on what has already been discovered, but to profit by that, and to go on to something beyond, not to conquer an adversary by disputing, but to conquer nature by working not to opine probably and prettily, but to know certainly and demonstrably, let such, as being true sons of nature, if they will consent to do so, join themselves to us. So that, leaving the porch of nature which endless multitudes have so long trod, we may at last open a way to the inner courts, and that we may mark the two ways, that old one and our new one by familiar names, we have been wont to call the one the anticipation of the mind, the other, the interpretation of nature, inst. Mag. Pref. Ad part. Roman 2. 13. Contents of the first volume. P. A just story of learning, containing the antiquities and originals of knowledges and their sects, their inventions, their diverse administrations and managings, their flourishings, their oppositions, decays, depressions, oblivions, removes, with the causes and occasions of them, and all other events concerning learning throughout all ages of the world, I may truly affirm to be wanting. The use and end of which work I do not so much design for curiosity or satisfaction of those that are the lovers of learning, but chiefly for a more serious and grave purpose, which is this, in few words, that it will make learned men more wise in the use and administration of learning. Bacon, Advancement of Learning, Book 2. 41. Introduction. It is my purpose to write the history of some of the most important of the physical sciences, from the earliest to the most recent periods. I shall thus have to trace some of the most remarkable branches of human knowledge, from their first germ to their growth into a vast and varied assemblage of undisputed truths, from the acute but fruitless essays of the early Greek philosophy to the comprehensive systems and demonstrated generalizations, which compose such sciences as the mechanics, astronomy, and chemistry of modern times. The completeness of historical view which belongs to such a design consists not in accumulating all the details of the cultivation of each science, but in marking the larger features of its formation. The historian must endeavor to point out how each of the important advances was made, by which the sciences have reached their present position, and when and by whom each of the valuable truths was obtained, of which the aggregate now constitutes a costly treasure. Such a task, if fitly executed, must have a well-founded interest for all those who look at the existing condition of human knowledge with complacency and admiration. The present generation finds itself the heir of a vast patrimony of science, and it must needs concern us to know the steps by which these possessions were acquired, and the documents by which they are secured to us and our heirs forever. Our species, from the time of its creation, has been traveling onwards in pursuit of truth. And now that we have reached a lofty and commanding position, with the broad light of day around us, it must be grateful to look back on the line of our vast progress, to review the journey, begun in early twilight amid primeval wilds, for a long time continued with slow advance and obscure prospects, and gradually and in later days followed along more open and lightsome paths in a wide and fertile region. The historian of science, from early periods to the present times, may hope for favor on the score of the mere subject of his narrative, and in virtue of the curiosity which the men, 42 of the present day, may naturally feel respecting the events and persons of his story. But such a survey may possess also an interest of another kind. It may be instructive as well as agreeable. It may bring before the reader the present form and extent, the future hopes and prospects of science, as well as its past progress. The eminence on which we stand may enable us to see the land of promise, as well as the wilderness through which we have passed. The examination of the steps by which our ancestors acquired our intellectual estate may make us acquainted with our expectations as well as our possessions, may not only remind us of what we have, but may teach us how to improve and increase our store. It will be universally expected that a history of inductive science should point out to us a philosophical distribution of the existing body of knowledge, and afford us some indication of the most promising mode of directing our future efforts to add to its extent and completeness. To deduce such lessons from the past history of human knowledge was the intention which originally gave rise to the present work. Nor is this portion of the design in any measure abandoned, but its execution, if it take place, must be attempted in a separate and future treatise on the philosophy of the inductive sciences. An essay of this kind may, I trust, from the progress already made in it, be laid before the public at no long interval after the present history. Note 1:1. The philosophy of the inductive sciences was published shortly after the present work. Though, therefore, many of the principles and maxims of such a work will disclose themselves with more or less of distinctness in the course of the history on which we are about to enter, the systematic and complete exposition of such principles must be reserved for this other treatise. My attempts and reflections have led me to the opinion that justice cannot be done to the subject without such a division of it. To this future work, then, I must refer the reader who is disposed to require, at the outset, a precise explanation of the terms which occur in my title. It is not possible, without entering into this philosophy, to explain adequately how science which is inductive differs from that which is not so, or why some portions of knowledge may properly be selected from the general mass and termed science. It will be sufficient at present to say that the sciences of which we have 43 here to treat are those which are commonly known as the physical sciences, and that by induction is to be understood that process of collecting general truths from the examination of particular facts, by which such sciences have been formed. There are, however, 2 or 3 remarks, of which the application will occur so frequently, and will tend so much to give us a clearer view of some of the subjects which occur in our history, that I will state them now in a brief and general manner. Facts and ideas in the first place, then, I remark that to the formation of science, 2 things are requisite: facts and ideas, observation of things without, and an inward effort of thought, or, in other words, sense and reason. Neither of these elements, by itself, can constitute substantial general knowledge. The impressions of sense, unconnected by some rational and speculative principle, can only end in a practical acquaintance with individual objects. The operations of the rational faculties, on the other hand, if allowed to go on without a constant reference to external things, can lead only to empty abstraction and barren ingenuity. Real speculative knowledge demands the combination of the 2 ingredients, right reason, and facts to reason upon. It has been well said that true knowledge is the interpretation of nature, and therefore it requires both the interpreting mind and nature for its subject, both the document and the ingenuity to read it aright. Thus invention, acuteness, and connection of thought are necessary on the one hand for the progress of philosophical knowledge, and on the other hand, the precise and steady application of these faculties to facts well known and clearly conceived. It is easy to point out instances in which science has failed to advance, in consequence of the absence of one or other of these requisites. Indeed, by far the greater part of the course of the world, the history of most times and most countries, exhibits a condition thus stationary with respect to knowledge. The facts, the impressions on the senses, on which the first successful attempts at physical knowledge proceeded, were as well known long before the time when they were thus turned to account, as at that period. The motions of the stars and the effects of weight were familiar to man before the rise of the Greek astronomy and mechanics, but the diviner mind was still absent. The act of thought had not been exerted, by which these facts were bound together under the form of laws and principles. And even at 44 this day, the tribes of uncivilized and half-civilized man over the whole face of the earth have before their eyes a vast body of facts, of exactly the same nature as those with which Europe has built the stately fabric of her physical philosophy. But in almost every other part of the earth, the process of the intellect by which these facts become science is unknown. The scientific faculty does not work. The scattered stones are there, but the builder's hand is wanting. And again, we have no lack of proof that mere activity of thought is equally inefficient in producing real knowledge. Almost the whole of the career of the Greek schools of philosophy, of the schoolmen of Europe in the Middle Ages, of the Arabian and Indian philosophers, shows us that we may have extreme ingenuity and subtlety, invention and connection, demonstration and method, and yet that out of these germs no physical science may be developed. We may obtain, by such means, logic and metaphysics, and even geometry and algebra. But out of such materials we shall never form mechanics and optics, chemistry and physiology. How impossible the formation of these sciences is without a constant and careful reference to observation and experiment. How rapid and prosperous their progress may be when they draw from such sources the materials on which the mind of the philosopher employs itself. The history of those branches of knowledge for the last 300 years abundantly teaches us. Note 2:1, for the antithesis of facts and ideas, see the Philosophy, Book 1, ch. 1245. Accordingly, the existence of clear ideas applied to distinct facts will be discernible in the history of science, whenever any marked advance takes place. And in tracing the progress of the various provinces of knowledge which come under our survey, it will be important for us to see that, at all such epochs, such a combination has occurred. That whenever any material step in general knowledge has been made, whenever any philosophical discovery arrests our attention, some man or men come before us, who have possessed, in an eminent degree, a clearness of the ideas which belong to the subject in question, and who have applied such ideas in a vigorous and distinct manner to ascertained facts and exact observations. We shall never proceed through any considerable range of our narrative without having occasion to remind the reader of this reflection. Successive steps in science. But there is another remark which we must also make. Such sciences as we have here to do with are 45, commonly, not formed by a single act. They are not completed by the discovery of one great principle. On the contrary, they consist in a long-continued advance, a series of changes, a repeated progress from one principle to another, different and often apparently contradictory. Now, it is important to remember that this contradiction is apparent only. The principles which constituted the triumph of the preceding stages of the science may appear to be subverted and ejected by the later discoveries, but in fact they are, so far as they were true, taken up in the subsequent doctrines and included in them. They continue to be an essential part of the science. The earlier truths are not expelled but absorbed, not contradicted but extended, and the history of each science, which may thus appear like a succession of revolutions, is, in reality, a series of developments. In the intellectual, as in the material world. Omnia mutantur nil interit. Nec manet ut furet nec formas servat eastum, sed tamen ipsa idem est. All changes, naught is lost. The forms are changed, and that which has been is not what it was, yet that which has been is. Nothing which was done was useless or unessential, though it ceases to be conspicuous and primary. Note 3:1, concerning successive generalizations in science, see the Philosophy, Book 1, ch. 2, sect. 11. Thus, the final form of each science contains the substance of each of its preceding modifications, and all that was at any antecedent period discovered and established ministers to the ultimate development of its proper branch of knowledge. Such previous doctrines may require to be made precise and definite, to have their superfluous and arbitrary portions expunged, to be expressed in new language, to be taken up into the body of science by various processes. But they do not on such accounts cease to be true doctrines, or to form a portion of the essential constituents of our knowledge. Terms record discoveries. The modes in which the earlier truths of science are preserved in its later forms are indeed various. From being asserted at first as strange discoveries, such truths come at last to be implied as almost self-evident axioms. They are recorded by some familiar maxim, or perhaps by some new word or phrase, which becomes part of the current language of the philosophical world, and thus asserts a principle, while it appears merely to indicate a transient, 46, notion, preserves as well as expresses a truth and, like a medal of gold, is a treasure as well as a token. We shall frequently have to notice the manner in which great discoveries thus stamp their impress upon the terms of a science, and, like great political revolutions, are recorded by the change of the current coin which has accompanied them. Note 4:1, concerning technical terms, see Philosophy, Book 1, ch. 3. Generalization. The great changes which thus take place in the history of science, the revolutions of the intellectual world, have, as a usual and leading character, this, that they are steps of generalization, transitions from particular truths to others of a wider extent, in which the former are included. This progress of knowledge, from individual facts to universal laws, from particular propositions to general ones, and from these to others still more general, with reference to which the former generalizations are particular, is so far familiar to men's minds, that, without here entering into further explanation, its nature will be understood sufficiently to prepare the reader to recognize the exemplifications of such a process, which he will find at every step of our advance. Inductive epochs, preludes, sequels in our history, it is the progress of knowledge only which we have to attend to. This is the main action of our drama, and all the events which do not bear upon this, though they may relate to the cultivation and the cultivators of philosophy, are not a necessary part of our theme. Our narrative will therefore consist mainly of successive steps of generalization, such as have just been mentioned. But among these, we shall find some of eminent and decisive importance, which have more peculiarly influenced the fortunes of physical philosophy, and to which we may consider the rest as subordinate and auxiliary. These primary movements, when the inductive process, by which science is formed, has been exercised in a more energetic and powerful manner, may be distinguished as the inductive epochs of scientific history, and they deserve our more express and pointed notice. They are, for the most part, marked by the great discoveries and the great philosophical names which all civilized nations have agreed in admiring. But, when we examine more clearly the history of such discoveries, we find that these epochs have not occurred suddenly and without preparation. They have been preceded by a period, which we may call their prelude, during which the ideas and facts on which they turned were called into action, were gradually evolved into clearness and connection, permanency and certainty, till at last the discovery which marks the epoch seized and fixed forever the truth which had till then been obscurely, and 47 doubtfully discerned. And again, when this step has been made by the principal discoverers, there may generally be observed another period, which we may call the sequel of the epoch, during which the discovery has acquired a more perfect certainty and a more complete development among the leaders of the advance, has been diffused to the wider throng of the secondary cultivators of such knowledge, and traced into its distant consequences. This is a work, always of time and labor, often of difficulty and conflict. To distribute the history of science into such epochs, with their preludes and sequels, if successfully attempted, must needs make the series and connections of its occurrences more distinct and intelligible. Such periods form resting places, where we pause till the dust of the confused march is laid, and the prospect of the path is clear. Inductive chart. Since the advance of science consists in collecting by induction true general laws from particular facts, and in combining several such laws into one higher generalization, in which they still retain their truth, we might form a chart, or table, of the progress of each science, by setting down the particular facts which have thus been combined, so as to form general truths, and by marking the further union of these general truths into others more comprehensive. The table of the progress of any science would thus resemble the map of a river, in which the waters from separate sources unite and make rivulets, which again meet with rivulets from other fountains, and thus go on forming by their junction trunks of a higher and higher order. The representation of the state of a science in this form would necessarily exhibit all the principal doctrines of the science, for each general truth contains the particular truths from which it was derived, and may be followed backwards till we have these before us in their separate state. And the last and most advanced generalization would have, in such a scheme, its proper place and the evidence of its validity. Hence, such an inductive table of each science would afford a criterion of the correctness of our distribution of the inductive epochs, by its coincidence with the views of the best judges, as to the substantial contents of the science in question. By forming, therefore, such inductive tables of the principal sciences of which I have here to speak, and by regulating by these tables my views of the history of the sciences, I conceive that I have secured the distribution of my 48 history from material error. For no merely arbitrary division of the events could satisfy such conditions. But though I have constructed such charts to direct the course of the present history, I shall not insert them in the work, reserving them for the illustration of the philosophy of the subject. For to this they more properly belong, being a part of the logic of induction. Note 5/1, inductive charts of the history of astronomy and of optics, such as are here referred to, are given in the Philosophy, Book 11, ch. 6. Stationary periods by the lines of such maps the real advance of science is depicted, and nothing else. But there are several occurrences of other kinds, too interesting and too instructive to be altogether omitted. In order to understand the conditions of the progress of knowledge, we must attend, in some measure, to the failures as well as the successes by which such attempts have been attended. When we reflect during how small a portion of the whole history of human speculations, science has really been, in any marked degree, progressive, we must needs feel some curiosity to know what was doing in these stationary periods. What field could be found which admitted of so wide a deviation, or at least so protracted a wandering? It is highly necessary to our purpose to describe the baffled enterprises as well as the achievements of human speculation. Deduction during a great part of such stationary periods, we shall find that the process which we have spoken of as essential to the formation of real science, the conjunction of clear ideas with distinct facts, was interrupted, and, in such cases, men dealt with ideas alone. They employed themselves in reasoning from principles, and they arranged, and classified, and analyzed their ideas so as to make their reasoning satisfy the requisitions of our rational faculties. This process of drawing conclusions from our principles by rigorous and unimpeachable trains of demonstration is termed deduction. In its due place, it is a highly important part of every science, but it has no value when the fundamental principles, on which the whole of the demonstration rests, have not first been obtained by the induction of facts, so as to supply the materials of substantial truth. Without such materials, a series of demonstrations resembles physical science only as a shadow resembles a real object. To give a real significance to our propositions, induction must provide what deduction cannot supply. From a pictured hook, we can hang only a pictured chain. Distinction of common notions and scientific ideas when, the 49 notions with which men are conversant in the common course of practical life, which give meaning to their familiar language and employment to their hourly thoughts, are compared with the ideas on which exact science is founded, we find that the two classes of intellectual operations have much that is common and much that is different. Without here attempting fully to explain this relation, which, indeed, is one of the hardest problems of our philosophy, we may observe that they have this in common, that both are acquired by acts of the mind exercised in connecting external impressions, and may be employed in conducting a train of reasoning. Or, speaking loosely, for we cannot here pursue the subject so as to arrive at philosophical exactness, we may say that all notions and ideas are obtained by an inductive and may be used in a deductive process. But scientific ideas and common notions differ in this, that the former are precise and stable, the latter vague and variable. The former are possessed with clear insight and employed in a sense rigorously limited and always identically the same. The latter have grown up in the mind from 1,000 dim and diverse suggestions, and the obscurity and incongruity which belong to their origin hang about all their applications. Scientific ideas can often be adequately exhibited for all the purposes of reasoning, by means of definitions and axioms. All attempts to reason by means of definitions from common notions lead to empty forms or entire confusion. Note 6/1, scientific ideas depend upon certain fundamental ideas which are enumerated in the Philosophy, Book 1, ch. 8. Such common notions are sufficient for the common practical conduct of human life, but man is not a practical creature merely. He has within him a speculative tendency, a pleasure in the contemplation of ideal relations, a love of knowledge as knowledge. It is this speculative tendency which brings to light the difference of common notions and scientific ideas of which we have spoken. The mind analyzes such notions, reasons upon them, combines and connects them, for it feels assured that intellectual things ought to be able to bear such handling. Even practical knowledge, we see clearly, is not possible without the use of the reason, and the speculative reason is only the reason satisfying itself of its own consistency. The speculative faculty cannot be controlled from acting. The mind cannot but claim a right to speculate concerning all its own acts and creations. Yet, when it exercises this right upon its common practical notions, we find that it runs into barren abstractions and ever-occurring cycles of subtlety. Such notions are like waters naturally stagnant. However much we urge and agitate them, they only revolve in stationary, 50 whirlpools. But the mind is capable of acquiring scientific ideas, which are better fitted to undergo discussion and impulsion. When our speculations are duly fed from the springheads of observation and frequently drawn off into the region of applied science, we may have a living stream of consistent and progressive knowledge. That science may be both real as to its import and logical as to its form. The examples of many existing sciences sufficiently prove. School philosophy so long, however, as attempts are made to form sciences, without such a verification and realization of their fundamental ideas, there is, in the natural series of speculation, no self-correcting principle. A philosophy constructed on notions obscure, vague, and unsubstantial, and held in spite of the want of correspondence between its doctrines and the actual train of physical events, may long subsist and occupy men's minds. Such a philosophy must depend for its permanence upon the pleasure which men feel in tracing the operations of their own and other men's minds, and in reducing them to logical consistency and systematical arrangement. In these cases, the main subjects of attention are not external objects, but speculations previously delivered. The object is not to interpret nature, but man's mind. The opinions of the masters are the facts which the disciples endeavor to reduce to unity or to follow into consequences. A series of speculators who pursue such a course may properly be termed a school, and their philosophy a school philosophy. Whether their agreement in such a mode of seeking knowledge arise from personal communication and tradition, or be merely the result of a community of intellectual character and propensity. The two great periods of school philosophy. It will be recollected that we are here directing our attention mainly to physical science, were that of the Greeks and that of the Middle Ages, the period of the first waking of science and that of its midday slumber. What has been said thus briefly and imperfectly would require great detail and much explanation to give it its full significance and authority. But it seemed proper to state so much in this place, in order to render more intelligible and more instructive, at the first aspect, the view of the attempted or effected progress of science. It is, perhaps, a disadvantage inevitably attending an undertaking like the present, that it must set out with statements so abstract, and must present them without their adequate development and proof. Such an introduction, both in its character and its scale of execution, may be compared to the geographical sketch of a country, with which, 51, the historian of its fortunes often begins his narration. So much of metaphysics is as necessary to us as such a portion of geography is to the historian of an empire, and what has hitherto been said is intended as a slight outline of the geography of that intellectual world, of which we have here to study the history. The name which we have given to this history of the inductive sciences has the fault of seeming to exclude from the rank of inductive sciences those which are not included in the history, as ethnology and glossology, political economy, psychology. This exclusion I by no means wish to imply, but I could find no other way of compendiously describing my subject, which was intended to comprehend those sciences in which, by the observation of facts and the use of reason, systems of doctrine have been established which are universally received as truths among thoughtful men, and which may therefore be studied as examples of the manner in which truth is to be discovered. Perhaps a more exact description of the work would have been a history of the principal sciences hitherto established by induction. I may add that I do not include in the phrase inductive sciences the branches of pure mathematics, geometry, arithmetic, algebra, and the like, because, as I have elsewhere stated, Phil. Ind. Sc. Book 2, C1, these are not inductive but deductive sciences. They do not infer true theories from observed facts and more general from more limited laws, but they trace the conditions of all theory, the properties of space and number, and deduce results from ideas without the aid of experience. The history of these sciences is briefly given in chapters 13 and 14 of the second book of the philosophy just referred to. I may further add that the other work to which I refer, the philosophy of the Inductive Sciences, is in a great measure historical, no less than the present history. That work contains the history of the sciences so far as it depends on ideas. The present work contains the history so far as it depends upon observation. The two works resulted simultaneously from the same examination of the principal writers on science in all ages and may serve to supplement each other. 53. Book 1. History of the Greek School Philosophy, with reference to physical science. Tau ode sigma gamma letter 1F70, rho letter 1F00, rho chi letter 1F70, delta epsilon psi alpha tau omicron, nu alpha epsilon tau ode lambda ode alpha sigma. Tau ode sigma delta letter 1F72, kappa ode nu delta epsilon nu omicron sigma, kappa rho alpha tau, epsilon rho omicron letter 1FD6, sigma letter 1F00 delta alpha nu tau omicron sigma, delta letter 1FC6, sigma epsilon, nu letter 1F04 lambda omicron iota sigma. Letter 1F10, pi epsilon letter 1F76. Letter 1F10 mu beta omicron lambda omicron epsilon, kappa rho epsilon mu alpha sigma alpha nu, letter 1F00 gamma kappa epsilon rho alpha sigma, letter 1F55 pi epsilon rho theta epsilon nu, chi rho epsilon sigma epsilon alpha nu, chi epsilon iota rho epsilon sigma sigma iota, lambda alpha beta letter 1F7c, nu phi iota alpha lambda alpha nu, letter 1F00, rho chi letter 1F78 sigma. Letter 1F10 nu, pi rho epsilon mu nu letter 1F B3, pi alpha tau epsilon rho, omicron letter 1F50, rho alpha nu dota delta letter 1FB6, nu letter 1F10 gamma chi epsilon iota kappa epsilon rho alpha epsilon nu omicron nu, zeta letter 1FC6 nu alpha. Kappa alpha letter 1F76, letter 1F60 kappa epsilon pi omicron rho omicron epsilon sigma, kappa epsilon mu alpha tau omega nu, letter 1Fe5 iota pi alpha sigma. Letter 1F00 nu epsilon mu omega nu tau, letter 1F10 kappa alpha lambda epsilon iota, letter 1F00 mu alpha tau, epsilon letter 1F54, phi rho omicron nu alpha, kappa alpha letter 1F76 phi iota lambda iota alpha nu omicron sigma tau omicron iota omicron, mu omicron letter 1FD6, rho alpha nu pindar. Pyth. Roman 4, 124, 349. Whence came their voyage? Then what peril held with adamantine rivets firmly bound? Asterisk, but soon as on the vessel's bow the anchor was hung up, then took the leader on the prow in hands a golden cup, and on great Father Jove did call, and on the winds and waters all, swept by the hurrying blast, and on the nights and ocean ways, and on the fair auspicious days, and loved return at last. 55. Book 1. A. History of the Greek School Philosophy, with reference to physical science. Chapter 1. Prelude to the Greek School Philosophy. Sect 1. First attempts of the speculative faculty in physical inquiries. At an early period of history, there appeared in men a propensity to pursue speculative inquiries concerning the various parts and properties of the material world. What they saw excited them to meditate, to conjecture, and to reason. They endeavored to account for natural events, to trace their causes, to reduce them to their principles. This habit of mind, or at least that modification of it which we have here to consider, seems to have been first unfolded among the Greeks. And during that obscure introductory interval, which elapsed while the speculative tendencies of men were as yet hardly disentangled from the practical, those who were most eminent in such inquiries were distinguished by the same term of praise which is applied to sagacity in matters of action, and were called wise men sigma omicron, phi omicron letter 1F76. But when it came to be clearly felt by such persons that their endeavors were suggested by the love of knowledge, a motive different from the motives which lead to the wisdom of active life, a name was adopted of a more appropriate, as well as of a more modest signification, and they were termed philosophers or lovers of wisdom. This appellation is said to have been first assumed by Pythagoras. Yet he, in Herodotus, instead of having this title, is called a powerful sophist, letter 1F11 lambda lambda nu omega nu, omicron letter 1F50. tau letter 1 ff7 letter 1 f00, sigma theta epsilon nu epsilon sigma tau alpha tau letter 1 ff3, sigma omicron phi iota sigma tau letter 1 fc7 pi upsilon theta alpha gamma omicron rho letter 1 fc3. The historian using this word, as it would seem, without intending to imply that misuse of reason which the term afterwards came to denote. The historians of literature, 56, placed Pythagoras at the origin of the Italic school, one of the two main lines of succession of the early Greek philosophers. But the other, the Ionic school, which more peculiarly demands our attention, in consequence of its character and subsequent progress, is deduced from Thales, who preceded the age of philosophy and was one of the Sophi, or wise men of Greece. The Ionic school was succeeded in Greece by several others, and the subjects which occupied the attention of these schools became very extensive. In fact, the first attempts were to form systems which should explain the laws and causes of the material universe, and to these were soon added all the great questions which our moral condition and faculties suggest. The physical philosophy of these schools is especially deserving of our study, as exhibiting the character and fortunes of the most memorable attempt at universal knowledge which has ever been made. It is highly instructive to trace the principles of this undertaking, for the course pursued was certainly one of the most natural and tempting which can be imagined. It was made by a nation unequaled in fine mental endowments at the period of its greatest activity and vigor. And yet it must be allowed, for, at least so far as physical science is concerned, none will contest this, to have been entirely unsuccessful. We cannot consider otherwise than as an utter failure, and endeavor to discover the causes of things, of which the most complete results are the Aristotelian physical treatises, and which, after reaching the point which these treatises mark, left the human mind to remain stationary, at any rate on all such subjects, for nearly 2,000 years. The early philosophers of Greece entered upon the work of physical speculation in a manner which showed the vigor and confidence of the questioning spirit, as yet untamed by labors and reverses. It was for later ages to learn that man must acquire, slowly and patiently, letter by letter, the alphabet in which nature writes her answers to such inquiries. The first students wished to divine, at a single glance, the whole import of her book. They endeavored to discover the origin and principle of the universe. According to Thales, water was the origin of all things, according to Anaximenes, air, and Heraclitus considered fire as the essential principle of the universe. It has been conjectured, with great plausibility, that this tendency to give to their philosophy the form of a cosmogony was owing to the influence of the poetical cosmogonies and theogonies which had been produced and admired at a still earlier age. Indeed, such wide and ambitious, 57 doctrines as those which have been mentioned were better suited to the dim magnificence of poetry than to the purpose of a philosophy which was to bear the sharp scrutiny of reason. When we speak of the principles of things, the term, even now, is very ambiguous and indefinite in its import, but how much more was that the case in the first attempts to use such abstractions? The term which is commonly used in this sense, letter 1F00, rho chi letter 1F74, signified at first the beginning, and in its early philosophical applications implied some obscure mixed reference to the mechanical, chemical, organic, and historical causes of the visible state of things, besides the theological views which at this period were only just beginning to be separated from the physical. Hence we are not to be surprised if the sources from which the opinions of this period appear to be derived are rather vague suggestions and casual analogies than any reasons which will bear examination. Aristotle conjectures, with considerable probability, that the doctrine of Thales, according to which water was the universal element, resulted from the manifest importance of moisture in the support of animal and vegetable life. But such precarious analyses of these obscure and loose dogmas of early antiquity are of small consequence to our object. In more limited and more definite examples of inquiry concerning the causes of natural appearances, and in the attempts made to satisfy men's curiosity in such cases, we appear to discern a more genuine prelude to the true spirit of physical inquiry. One of the most remarkable instances of this kind is to be found in the speculations which Herodotus records, relative to the cause of the floods of the Nile. Concerning the nature of this river, says the father of history, I was not able to learn anything, either from the priests or from anyone besides, though I questioned them very pressingly. For the Nile is flooded for 100 days, beginning with the summer solstice, and after this time it diminishes, and is, during the whole winter, very small. And on this head, I was not able to obtain anything satisfactory from any one of the Egyptians, when I asked what is the power by which the Nile is, in its nature, the reverse of other rivers. We may see, I think, in the historian's account, that the Grecian mind felt a craving to discover the reasons of things which other nations did not feel. The Egyptians, it appears, had no theory and felt no want of a theory. Not so the Greeks. They had their reasons to render, though they were not such as satisfied Herodotus. Some 58 of the Greeks, he says, who wished to be considered great philosophers, letter 1 F11 lambda lambda nu omega nu, tau ot nu epsilon sigma, letter 1 F10 pi ot sigma eta mu omicron iota, beta omicron epsilon lambda omicron mu epsilon nu omicron iota, gamma epsilon nu epsilon sigma theta alpha iota, sigma omicron phi iota eta nu, have propounded 3 ways of accounting for these floods. 2 of them, he adds, I do not think worthy of record, except just so far as to mention them. But as these are some of the earliest Greek essays in physical philosophy, it will be worthwhile, even at this day, to preserve the brief notice he has given of them, and his own reasonings upon the same subject. One of these opinions holds that the Etesian winds which blew from the north are the cause of these floods, by preventing the Nile from flowing into the sea. Against this, the historian reasons very simply and sensibly. Very often when the Etesian winds do not blow, the Nile is flooded nevertheless. And moreover, if the Etesian winds were the cause, all other rivers, which have their course opposite to these winds, ought to undergo the same changes as the Nile, which the rivers of Syria and Libya so circumstanced do not. The next opinion is still more unscientific, letter 1 F00 nu epsilon pi iota sigma tau eta mu omicron nu epsilon sigma tau epsilon rho eta, and is, in truth, marvelous for its folly. This holds that the ocean flows all round the earth, and that the Nile comes out of the ocean, and by that means produces its effects. Now, says the historian, the man who talks about this ocean river goes into the region of fable, where it is not easy to demonstrate that he is wrong. I know of no such river, but I suppose that Homer and some of the earlier poets invented this fiction and introduced it into their poetry. He then proceeds to a third account, which to a modern reasoner would appear not at all unphilosophical in itself, but which he nevertheless rejects in a manner no less decided than the others. The third opinion, though much the most plausible, is still more wrong than the others, for it asserts an impossibility, namely, that the Nile proceeds from the melting of the snow. Now the Nile flows out of Libya and through Ethiopia, which are very hot countries, and thus comes into Egypt, which is a colder region. How then can it proceed from snow? He then offers several other reasons to show, as he says, to any one capable of reasoning on such subjects, letter 1 F00 nu delta rho iota, gamma epsilon lambda omicron gamma iota zeta epsilon sigma theta alpha iota, tau omicron iota omicron epsilon tau omega nu, pi epsilon rho iota omicron letter 1 F35 letter 1 FF3, tau epsilon letter 1 F14 omicron nu tau iota, that the assertion cannot be true. The winds which blow from the southern regions are hot, the inhabitants are black. The swallows and kites, letter 1 F30 kappa tau letter 1 FD6 nu omicron iota, stay in the country the whole year. The cranes fly the colds of Scythia and seek their warm winter quarters there, which would not be if it snowed ever so little. He adds another reason, founded apparently upon 59, some limited empirical maxim of weather wisdom taken from the climate of Greece. Libya, he said, has neither rain nor ice, and therefore no snow, for in 5 days after a fall of snow, there must be a fall of rain, so that if it snowed in those regions, it must rain too. I need not observe that Herodotus was not aware of the difference between the climate of high mountains and plains in a torrid region, but it is impossible not to be struck both with the activity and the coherency of thought displayed by the Greek mind in this primitive physical inquiry. But I must not omit the hypothesis which Herodotus himself proposes, after rejecting those which have been already given. It does not appear to me easy to catch his exact meaning, but the statement will still be curious. If, he says, one who has condemned opinions previously promulgated may put forward his own opinion concerning so obscure a matter, I will state why it seems to me that the Nile is flooded in summer. This opinion he propounds at first with an oracular brevity, which it is difficult to suppose that he did not intend to be impressive. In winter, the sun is carried by the seasons away from his former course, and goes to the upper parts of Libya, and there, in short, is the whole account. For that region to which this divinity, the sun, is nearest, must naturally be most scant of water, and the river sources of that country must be dried up. But the lively and garrulous Ionian immediately relaxes from this apparent reserve. To explain the matter more at length, he proceeds, it is thus. The sun, when he traverses the upper parts of Libya, does what he commonly does in summer. He draws the water to him, letter 1F15 lambda cap epsilon iota, letter 1F10 pi. Letter 1F11 omega upsilon tau, letter 1F78 nu tau, letter 1F78, letter 1F55 delta omega rho. And having thus drawn it, he pushes it to the upper regions of the air probably. And then the winds take it and disperse it till they dissolve in moisture. And thus the winds which blow from those countries, Libs and Notus, are the most moist of all winds. Now when the winter relaxes and the sun returns to the north, he still draws water from all the rivers, but they are increased by showers and rain torrents so that they are in flood till the summer comes. And then, the rain falling and the sun still drawing them, they become small. But the Nile, not being fed by rains, yet being drawn by the sun, is alone of all rivers much more scanty in the winter than in the summer. For in summer it is drawn like all other rivers, but in winter it alone has its supplies shut up. And in this way, I have been led to think the sun is the cause of the occurrence in question. We may remark that the historian here appears to ascribe the inequality of the Nile at different seasons to the influence of the sun upon its springs alone, the other cause of change, the rains being here excluded. And that, on this supposition, the same relative effects would be produced whether the sun increased the sources in winter by melting the snows, or diminished them in summer by what he calls drawing them upwards. This specimen of the early efforts of the Greeks in physical speculations appears to me to speak strongly for the opinion that their philosophy on such subjects was the native growth of the Greek mind, and owed nothing to the supposed lore of Egypt and the East, an opinion which has been adopted with regard to the Greek philosophy in general by the most competent judges on a full survey of the evidence. Indeed, we have no evidence whatever that, at any period, the African or Asiatic nations, with the exception perhaps of the Indians, ever felt this importunate curiosity with regard to the definite application of the idea of cause and effect to visible phenomena, or drew so strong a line between a fabulous legend and a reason rendered, or attempted to ascend to a natural cause by classing together phenomena of the same kind. We may be well excused, therefore, for believing that they could not impart to the Greeks what they themselves did not possess. And so far as our survey goes, physical philosophy has its origin, apparently spontaneous and independent, in the active and acute intellect of Greece. Note 11/1, Thirlwall Hist, Gr. Roman 2, 130, and as their quoted Ritter Geschichte der Philosophie, I 159-173. Sect 2, Primitive Mistake in Greek Physical Philosophy. We now proceed to examine with what success the Greeks followed the track into which they had thus struck. And here we are obliged to confess that they very soon turned aside from the right road to truth and deviated into a vast field of error, in which they and their successors have wandered almost to the present time. It is not necessary here to inquire why those faculties which appear to be bestowed upon us for the discovery of truth were permitted by Providence to fail so signally in answering that purpose, whether, like the powers by which we seek our happiness, they involve a responsibility on our part and may be defeated by rejecting the guidance of a higher faculty, or whether these endowments, though they did not 61 immediately lead man to profound physical knowledge, answered some nobler and better purpose in his constitution and government. The fact undoubtedly was that the physical philosophy of the Greeks soon became trifling and worthless, and it is proper to point out, as precisely as we can, in what the fundamental mistake consisted. To explain this, we may in the first place return for a moment to Herodotus's account of the cause of the floods of the Nile. The reader will probably have observed a remarkable phrase used by Herodotus in his own explanation of these inundations. He says that the sun draws or attracts the water, a metaphorical term obviously intended to denote some more general and abstract conception than that of the visible operation which the word primarily signifies. This abstract notion of drawing is, in the historian, as we see, very vague and loose. It might, with equal propriety, be explained to mean what we now understand by mechanical or by chemical attraction, or pressure, or evaporation. And in like manner, all the first attempts to comprehend the operations of nature led to the introduction of abstract conceptions, often vague indeed, but not therefore unmeaning, such as motion and velocity, force and pressure, impetus and momentum, letter 1Fe5 omicron pi letter 1F74. And the next step in philosophizing necessarily was to endeavor to make these vague abstractions more clear and fixed, so that the logical faculty should be able to employ them securely and coherently. But there were two ways of making this attempt. The one, by examining the words only and the thoughts which they call up; the other, by attending to the facts and things which bring these abstract terms into use. The latter, the method of real inquiry, was the way to success, but the Greeks followed the former, the verbal or notional course, and failed. If Herodotus, when the notion of the sun's attracting the waters of rivers had entered into his mind, had gone on to instruct himself, by attention to facts, in what manner this notion could be made more definite, while it still remained applicable to all the knowledge which could be obtained, he would have made some progress towards a true solution of his problem. If, for instance, he had tried to ascertain whether this attraction which the sun exerted upon the waters of rivers depended on his influence at their fountains only, or was exerted over their whole course, and over waters which were not parts of rivers, he would have been led to reject his hypothesis. For he would have found, by observations sufficiently obvious, that the sun's attraction, as shown in such cases, is a tendency to lessen all expanded and 62 open collections of moisture, whether flowing from a spring or not. And it would then be seen that this influence, operating on the whole surface of the Nile, must diminish it as well as other rivers in summer, and therefore could not be the cause of its overflow. He would thus have corrected his first loose conjecture by a real study of nature, and might, in the course of his meditations, have been led to available notions of evaporation or other natural actions. And, in like manner, in other cases, the rude attempts at explanation, which the first exercise of the speculative faculty produced, might have been gradually concentrated and refined, so as to fall in, both with the requisitions of reason and the testimony of sense. But this was not the direction which the Greek speculators took. On the contrary, as soon as they had introduced into their philosophy any abstract and general conceptions, they proceeded to scrutinize these by the internal light of the mind alone, without any longer looking abroad into the world of sense. They took for granted that philosophy must result from the relations of those notions which are involved in the common use of language, and they proceeded to seek their philosophical doctrines by studying such notions. They ought to have reformed and fixed their usual conceptions by observation. They only analyzed and expanded them by reflection. They ought to have sought by trial, among the notions which passed through their minds, some one which admitted of exact application to facts. They selected arbitrarily, and, consequently, erroneously, the notions according to which facts should be assembled and arranged. They ought to have collected clear fundamental ideas from the world of things by inductive acts of thought. They only derived results by deduction from one or other of their familiar conceptions. Note 12:1. The course by which the sciences were formed, and which is here referred to as that which the Greeks did not follow, is described in detail in the Philosophy, Book 11, of the Construction of Science. When this false direction had been extensively adopted by the Greek philosophers, we may treat of it as the method of their schools. Under that title, we must give a further account of it. 63. Chapter 2. The Greek School Philosophy. Sect 1. The general foundation of the Greek school philosophy. The physical philosophy of the Greek schools was formed by looking at the material world through the medium of that common language which men employ to answer the common occasions of life, and by adopting, arbitrarily, as the grounds of comparison of facts, and of inference from them, notions more abstract and large than those with which men are practically familiar, but not less vague and obscure. Such a philosophy, however much it might be systematized, by classifying and analyzing the conceptions which it involves, could not overcome the vices of its fundamental principle. But before speaking of these defects, we must give some indications of its character. The propensity to seek for principles in the common usages of language may be discerned at a very early period. Thus we have an example of it in a saying which is reported of Thales, the founder of Greek philosophy. When he was asked, "What is the greatest thing?" he replied, "Place, for all other things are in the world, but the world is in it." In Aristotle, we have the consummation of this mode of speculation. The usual point from which he starts in his inquiries is that we say thus or thus in common language. Thus, when he has to discuss the question whether there be, in any part of the universe, a void or space in which there is nothing, he inquires first in how many senses we say that one thing is in another. He enumerates many of these. We say the part is in the whole, as the finger is in the hand. Again we say the species is in the genus, as man is included in animal. Again, the government of Greece is in the king, and various other senses are described or exemplified, but of all these the most proper is when we say a thing is in a vessel, and generally in place. He next examines what place is and comes to this conclusion, that if about a body there be another body including it, it is in place, and if not, not. A body moves when it changes its place. But 64 he adds that if water be in a vessel, the vessel being at rest, the parts of the water may still move, for they are included by each other. So that while the whole does not change its place, the parts may change their places in a circular order. Proceeding then to the question of a void, he, as usual, examines the different senses in which the term is used, and adopts, as the most proper, place without matter, with no useful result, as we shall soon see. Again, in a question concerning mechanical action, he says, "When a man moves a stone by pushing it with a stick, we say both that the man moves the stone and that the stick moves the stone, but the latter more properly." Again, we find the Greek philosophers applying themselves to extract their dogmas from the most general and abstract notions which they could detect. For example, from the conception of the universe as one or as many things. They try to determine how far we may, or must, combine with these conceptions that of a whole, of parts, of number, of limits, of place, of beginning or end, of full or void, of rest or motion, of cause and effect, and the like. The analysis of such conceptions with such a view occupies, for instance, almost the whole of Aristotle's treatise on the heavens. The dialogue of Plato, which is entitled Parmenides, appears at first as if its object were to show the futility of this method of philosophizing. For the philosopher whose name it bears is represented as arguing with an Athenian named Aristotle, and by a process of metaphysical analysis, reducing him at least to this conclusion, that whether one exist or do not exist, it follows that both it and other things, with reference to themselves and to each other, all and in all respects, both are and are not, both appear and appear not. Yet the method of Plato, so far as concerns truths of that kind with which we are here concerned, was little more efficacious than that of his rival. It consists mainly, as may be seen in several of the dialogues, and especially in the Timaeus, in the application of notions as loose as those of the Peripatetics. For example, the conceptions of the good, the beautiful, the perfect, and these are rendered still more arbitrary by assuming an acquaintance with the views of the creator of the universe. The philosopher is thus led to maxims which agree with those 65 of the Aristotelians, that there can be no void, that things seek their own place, and the like. Note 16:1. This Aristotle is not the Stagirite, who was 45 years younger than Plato, but one of the 30 tyrants, as they were called. Another mode of reasoning, very widely applied in these attempts, was the doctrine of contrarieties, in which it was assumed that adjectives or substantives which are in common language, or in some abstract mode of conception, opposed to each other, must point at some fundamental antithesis in nature, which it is important to study. Thus Aristotle says that the Pythagoreans, from the contrasts which number suggests, collected 10 principles, limited and unlimited, odd and even, one and many, right and left, male and female, rest and motion, straight and curved, light and darkness, good and evil, square and oblong. We shall see hereafter that Aristotle himself deduced the doctrine of 4 elements, and other dogmas by oppositions of the same kind. The physical speculator of the present day will learn without surprise that such a mode of discussion as this led to no truths of real or permanent value. The whole mass of the Greek philosophy, therefore, shrinks into an almost imperceptible compass when viewed with reference to the progress of physical knowledge. Still, the general character of this system, and its fortunes from the time of its founders to the overthrow of their authority, are not without their instruction, and, it may be hoped, not without their interest. I proceed, therefore, to give some account of these doctrines in their most fully developed and permanently received form, that in which they were presented by Aristotle. Sect 2. The Aristotelian Physical Philosophy. The principal physical treatises of Aristotle are the 8 books of Physical Lectures, the 4 books of the Heavens, the 2 books of Production and Destruction. For the Book of the World is now universally acknowledged to be spurious, and the Meteorologies, though full of physical explanations of natural phenomena, does not exhibit the doctrines and reasonings of the school in so general a form. The same may be said of the mechanical problems. The treatises on the various subjects of natural history, on animals, on the parts of animals, on plants, on physiognomonics, on colors, on sound, contain an extraordinary 66 accumulation of facts and manifest a wonderful power of systematizing, but are not works which expound principles, and therefore do not require to be here considered. The Physical Lectures are possibly the work concerning which a well-known anecdote is related by Simplicius, a Greek commentator of the 6th century, as well as by Plutarch. It is said that Alexander the Great wrote to his former tutor to this effect: "You have not done well in publishing these lectures, for how shall we, your pupils, excel other men if you make that public to all, which we learnt from you?" To this Aristotle is said to have replied, "My lectures are published and not published. They will be intelligible to those who heard them, and to none besides." This may very easily be a story invented and circulated among those who found the work beyond their comprehension, and it cannot be denied that to make out the meaning and reasoning of every part would be a task very laborious and difficult, if not impossible. But we may follow the import of a large portion of the Physical Lectures with sufficient clearness to apprehend the character and principles of the reasoning, and this is what I shall endeavor to do. The author's introductory statement of his view of the nature of philosophy falls in very closely with what has been said, that he takes his facts and generalizations as they are implied in the structure of language. We must in all cases proceed, he says, from what is known to what is unknown. This will not be denied, but we can hardly follow him in his inference. He adds, we must proceed, therefore, from universal to particular. And something of this, he pursues, may be seen in language, for names signify things in a general and indefinite manner, as circle, and by defining we unfold them into particulars. He illustrates this by saying, "Thus children at first call all men father and all women mother, but afterwards distinguish." In accordance with this view, he endeavors to settle several of the great questions concerning the universe, which had been started among subtle and speculative men, by unfolding the meaning of the words and phrases which are applied to the most general notions of things and relations. We have already noticed this method. A few examples will illustrate it further. Whether there was or was not a void, or place without matter, had already been debated among rival sects of philosophers. The antagonist arguments were briefly these: there must be a void, because a body cannot move into a space except it is 67 empty, and therefore without a void there could be no motion, and, on the other hand, there is no void, for the intervals between bodies are filled with air, and air is something. These opinions had even been supported by reference to experiment. On the one hand, Anaxagoras and his school had shown that air, when confined, resisted compression by squeezing a blown bladder and pressing down an inverted vessel in the water. On the other hand, it was alleged that a vessel full of fine ashes held as much water as if the ashes were not there, which could only be explained by supposing void spaces among the ashes. Aristotle decides that there is no void, on such arguments as this. In a void there could be no difference of up and down, for as in nothing there are no differences, so there are none in a privation or negation. But a void is merely a privation or negation of matter. Therefore, in a void, bodies could not move up and down, which it is in their nature to do. It is easily seen that such a mode of reasoning, elevates the familiar forms of language and the intellectual connections of terms to a supremacy over facts, making truth depend upon whether terms are or are not privative, and whether we say that bodies fall naturally. In such a philosophy, every new result of observation would be compelled to conform to the usual combinations of phrases, as these had become associated by the modes of apprehension previously familiar. It is not intended here to intimate that the common modes of apprehension, which are the basis of common language, are limited and casual. They imply, on the contrary, universal and necessary conditions of our perceptions and conceptions. Thus, all things are necessarily apprehended as existing in time and space, and as connected by relations of cause and effect. And so far as the Aristotelian philosophy reasons from these assumptions, it has a real foundation, though even in this case the conclusions are often insecure. We have an example of this reasoning in the 8th book, where he proves that there never was a time in which change and motion did not exist. For if all things were at rest, the first motion must have been produced by some change in some of these things. That is, there must have been a change before the first change. And again, how can before and after apply when time is not? Or how can time be when motion is not, if, he adds, time is a numeration of motion, and if time be eternal, motion must be eternal. But he sometimes, 68, introduces principles of a more arbitrary character, and besides the general relations of thought takes for granted the inventions of previous speculators, such, for instance, as the then commonly received opinions concerning the frame of the world. From the assertion that motion is eternal, proved in the manner just stated, Aristotle proceeds by a curious train of reasoning to identify this eternal motion with the diurnal motion of the heavens. There must, he says, be something which is the first mover. This follows from the relation of causes and effects. Again, motion must go on constantly, and therefore must be either continuous or successive. Now what is continuous is more properly said to take place constantly than what is successive. Also, the continuous is better, but we always suppose that which is better to take place in nature, if it be possible. The motion of the first mover will, therefore, be continuous, if such an eternal motion be possible. We here see the vague judgment of better and worse introduced, as that of natural and unnatural was before, into physical reasonings. I proceed with Aristotle's argument. We have now, therefore, to show that there may be an infinite single, continuous motion, and that this is circular. This is, in fact, proved, as may readily be conceived, from the consideration that a body may go on perpetually revolving uniformly in a circle. And thus we have a demonstration on the principles of this philosophy that there is and must be a first mover revolving eternally with a uniform circular motion. Though this kind of philosophy may appear too trifling to deserve being dwelt upon, it is important for our purpose so far as to exemplify it, that we may afterwards advance, confident that we have done it no injustice. I will now pass from the doctrines relating to the motions of the heavens to those which concern the material elements of the universe. And here it may be remarked that the tendency, of which we are here tracing the development, to extract speculative opinions from the relations of words, must be very natural to man. For the very widely accepted doctrine of the four elements, which appears to be founded on the opposition of the adjectives hot and cold, wet and dry, is much older than Aristotle, and was probably one of the earliest of philosophical dogmas. The great master of this philosophy, however, puts the opinion in a more systematic manner than his predecessors. 69. We seek, he says, the principles of sensible things, that is, of tangible bodies. We must take, therefore, not all the contrarieties of quality, but those only which have reference to the touch. Thus black and white, sweet and bitter, do not differ as tangible qualities, and therefore must be rejected from our consideration. Now the contrarieties of quality which refer to the touch are these: hot, cold, dry, wet, heavy, light, hard, soft, unctuous, meager, rough, smooth, dense, rare. He then proceeds to reject all but the four first of these for various reasons: heavy and light, because they are not active and passive qualities; the others, because they are combinations of the four first, which therefore he infers to be the four elementary qualities. Now in four things there are 6 combinations of 2, but the combinations of 2 opposites, as hot and cold, must be rejected. We have therefore 4 elementary combinations, which agree with the 4 apparently elementary bodies. Fire is hot and dry, air is hot and wet, for steam is air. Water is cold and wet, earth is cold and dry. It may be remarked that this disposition to assume that some common elementary quality must exist in the cases in which we habitually apply a common adjective, as it began before the reign of the Aristotelian philosophy, so also survived its influence. Not to mention other cases, it would be difficult to free Bacon's inquisitio in naturam calidi, examination of the nature of heat, from the charge of confounding together very different classes of phenomena under the cover of the word hot. The correction of these opinions concerning the elementary composition of bodies belongs to an advanced period in the history of physical knowledge, even after the revival of its progress. But there are some of the Aristotelian doctrines which particularly deserve our attention, from the prominent share they had in the very first beginnings of that revival. I mean the doctrines concerning motion. These are still founded upon the same mode of reasoning from adjectives, but in this case, the result follows not only from the opposition of the words, but also from the distinction of their being absolutely or relatively true. Former writers, says Aristotle, have considered heavy and light relatively only, taking cases where both things have weight, but one is lighter than the other. And they imagined that, in 70, this way, they defined what was absolutely letter 1f0, 1 pi lambda letter 1f6 sigma heavy and light. We now know that things which rise by their lightness do so only because they are pressed upwards by heavier surrounding bodies. And this assumption of absolute levity, which is evidently gratuitous, or rather merely nominal, entirely vitiated the whole of the succeeding reasoning. The inference was that fire must be absolutely light, since it tends to take its place above the other three elements. Earth absolutely heavy, since it tends to take its place below fire, air, and water. The philosopher argued also, with great acuteness, that air, which tends to take its place below fire and above water, must do so by its nature, and not in virtue of any combination of heavy and light elements. For if air were composed of the parts which give fire its levity, joined with other parts which produce gravity, we might assume a quantity of air so large that it should be lighter than a small quantity of fire, having more of the light parts. It thus follows that each of the four elements tends to its own place, fire being the highest, air the next, water the next, and earth the lowest. The whole of this train of errors arises from fallacies which have a verbal origin, from considering light as opposite to heavy, and from considering levity as a quality of a body, instead of regarding it as the effect of surrounding bodies. It is worthwhile to notice that a difficulty which often embarrasses persons on their entrance upon physical speculations, the difficulty of conceiving that up and down are different directions in different places, had been completely got over by Aristotle and the Greek philosophers. They were steadily convinced of the roundness of the earth, and saw that this truth led to the conclusion that all heavy bodies tend, in converging directions, to the center. And they added, as the heavy tends to the center, the light tends to the exterior, for exterior is opposite to center as heavy is to light. The tendencies of bodies downwards and upwards, their weight, their fall, their floating or sinking, were thus accounted for in a manner which, however unsound, satisfied the greater part of the speculative world till the time of Galileo and Stevinus, though Archimedes in the meantime published the true theory of floating bodies, which is very different from that above stated. Other parts of the doctrines of motion were delivered by the Stagirite in the same spirit and with the same success. The motion of a body which is thrown along the 71 ground diminishes and finally ceases. The motion of a body which falls from a height goes on becoming quicker and quicker. This was accounted for on the usual principle of opposition, by saying that the former is a violent, the latter a natural motion. And the later writers of this school expressed the characters of such motions in verse. The rule of natural motion was principium tepit, medium cum fine calebit. Cool at the first, it warm and warmer glows, and of violent motion, the law was principium fervit, medium calit, ultima frigit. Hot at the first, then barely warm, then cold. It appears to have been considered by Aristotle a difficult problem to explain why a stone thrown from the hand continues to move for some time and then stops. If the hand was the cause of the motion, how could the stone move at all when left to itself? If not, why does it ever stop? And he answers this difficulty by saying that there is a motion communicated to the air, the successive parts of which urge the stone onwards, and that each part of this medium continues to act for some while after it has been acted on, and the motion ceases when it comes to a particle which cannot act after it has ceased to be acted on. It will be readily seen that the whole of this difficulty, concerning a body which moves forward and is retarded till it stops, arises from ascribing the retardation not to the real cause, the surrounding resistances, but to the body itself. One of the doctrines which was the subject of the warmest discussion between the defenders and opposers of Aristotle, at the revival of physical knowledge, was that in which he asserts, that body is heavier than another which in an equal bulk moves downward quicker. The opinion maintained by the ** Aristotelians at the time of Galileo was that bodies fall quicker exactly in proportion to their weight. The master himself asserts this in express terms and reasons upon it. Yet in another passage, he appears to distinguish between weight and actual motion downwards. In physics, we call bodies heavy and light from their power of motion, but these names are not applied to their actual operations. Letter 1F10 nu epsilon rho gam epsilon AO, alpha, O to sigma, except anyone thinks 72 momentum, letter 1Fe5 omicron pi letter 1F74, to be a word of both applications. But heavy and light are, as it were, the embers or sparks of motion, and therefore proper to be treated of here. The distinction just alluded to, between power or faculty of action, and actual operation or energy, is one very frequently referred to by Aristotle, and though not by any means useless, may easily be so used as to lead to mere verbal refinements instead of substantial knowledge. The Aristotelian distinction of causes has not any very immediate bearing upon the parts of physics of which we have here mainly spoken, but it was so extensively accepted and so long retained that it may be proper to notice it. One kind of cause is the matter of which anything is made, as bronze of a statue and silver of a vial. Another is the form and pattern, as the cause of an octave is the ratio of 2 to 1. Again, there is the cause which is the origin of the production, as the father of the child. And again, there is the end, or that for the sake of which anything is done, as health is the cause of walking. These 4 kinds of cause, the material, the formal, the efficient, and the final, were long leading points in all speculative inquiries, and our familiar forms of speech still retain traces of the influence of this division. It is my object here to present to the reader in an intelligible shape the principles and mode of reasoning of the Aristotelian philosophy, not its results. If this were not the case, it would be easy to excite a smile by insulating some of the passages which are most remote from modern notions. I will only mention, as specimens, 2 such passages, both very remarkable. In the beginning of the book on the heavens, he proves the world to be perfect by reasoning of the following kind. The bodies of which the world is composed are solids, and therefore have 3 dimensions. Now 3 is the most perfect number. It is the first of numbers, for of 1 we do not speak as a number, of 2 we say both, but 3 is the first number of which we say all. Moreover, it has a beginning, a middle, and an end. The reader will still perceive the verbal foundations of opinions thus supported. The simple elements must have simple motions, and thus fire and air have their natural motions upwards, and water and earth have, 73, their natural motions downwards. But besides these motions, there is motion in a circle, which is unnatural to these elements, but which is a more perfect motion than the other, because a circle is a perfect line, and a straight line is not. And there must be something to which this motion is natural. From this it is evident, he adds with obvious animation, that there is some essence of body different from those of the 4 elements, more divine than those and superior to them. If things which move in a circle move contrary to nature, it is marvelous, or rather absurd, that this, the unnatural motion, should alone be continuous and eternal, for unnatural motions decay speedily. And so, from all this, we must collect that besides the 4 elements which we have here and about us, there is another removed far off, and the more excellent in proportion as it is more distant from us. This 5th element was the quinta essentia, of after writers, of which we have a trace in our modern literature, in the word quintessence. Sect 3 technical forms of the Greek schools. We have hitherto considered only the principle of the Greek physics, which was, as we have seen, to deduce its doctrines by an analysis of the notions which common language involves. But though the Grecian philosopher began by studying words and their common meanings, he soon found himself led to fix upon some special shades or applications of these meanings as the permanent and standard notion, which they were to express. That is, he made his language technical. The invention and establishment of technical terms is an important step in any philosophy, true or false. We must, therefore, say a few words on this process, as exemplified in the ancient systems. One, technical forms of the Aristotelian philosophy. We have already had occasion to cite some of the distinctions introduced by Aristotle, which may be considered as technical. For instance, the classification of causes as material, formal, efficient, and final, and the opposition of qualities as absolute and relative. A few more of the most important examples may suffice. An analysis of objects into matter and form, when metaphorically extended from visible objects to things conceived in the most general manner, became an habitual hypothesis of the Aristotelian school. Indeed, this metaphor is even yet one of the most significant of those which we can employ, to suggest one of the most comprehensive and fundamental antitheses with which philosophy has to do, the opposition of sense and reason, of 74 impressions and laws. In this application, the German philosophers have, up to the present time, rested upon this distinction a great part of the weight of their systems. As when Kant says, that space and time are the forms of sensation. Even in our own language, we retain a trace of the influence of this Aristotelian notion, in the word information, when used for that knowledge which may be conceived as molding the mind into a definite shape, instead of leaving it a mere mass of unimpressed susceptibility. Another favorite Aristotelian antithesis is that of power and act, delta epsilon nu alpha mu iota sigma, letter 1f10 nu epsilon rho gamma epsilon iota alpha. This distinction is made the basis of most of the physical philosophy of the school, being, however, generally introduced with a peculiar limitation. Thus, light is defined to be the act of what is lucid, as being lucid. And if, it is added, the lucid be so in power but not in act, we have darkness. The reason of the limitation, as being lucid, is that a lucid body may act in other ways. Thus a torch may move as well as shine, but its moving is not its act as being a lucid body. Aristotle appears to be well satisfied with this explanation, for he goes on to say, thus light is not fire, nor any body whatever, or the emanation of any body, for that would be a kind of body, but it is the presence of something like fire in the body. It is, however, impossible that two bodies should exist in the same place, so that it is not a body. And this reasoning appears to leave him more satisfied with his doctrine, that light is an energy or act. But we have a more distinctly technical form given to this notion. Aristotle introduced a word formed by himself to express the act which is thus opposed to inactive power. This is the celebrated word letter 1f10 nu tau epsilon lambda epsilon chi epsilon iota alpha. Thus the noted definition of motion in the third book of the Physics is that it is the entelechy or act of a movable body in respect of being movable. And the definition of the soul is that it is the entelechy of a natural body which has life by reason of its power. This word has been variously translated by the followers of Aristotle, and some of them have declared it untranslatable. Act and action are held to be inadequate substitutes. The very act, ipse cursus actionis, is employed by some. Primus actus is employed by many, but another school use primus actus of a non-operating form. Beauteous uses efficacia. Cicero translates it, quasi quandam continuatum motionem, et perennem. But this paraphrase, though it may, 75, fall in with the description of the soul, which is the subject with which Cicero is concerned, does not appear to agree with the general applications of the term. Hermolaus Barbarus is said to have been so much oppressed with this difficulty of translation that he consulted the evil spirit by night, entreating to be supplied with a more common and familiar substitute for this word. The mocking fiend, however, suggested only a word equally obscure, and the translator, discontented with this, invented for himself the word perfecta habea. We need not here notice the endless apparatus of technicalities which was, in later days, introduced into the Aristotelian philosophy, but we may remark that their long continuance and extensive use show us how powerful technical phraseology is, for the perpetuation either of truth or error. The Aristotelian terms and the metaphysical views which they tend to preserve are not yet extinct among us. In a very recent age of our literature, it was thought a worthy employment by some of the greatest writers of the day to attempt to expel this system of technicalities by ridicule. Cramb regretted extremely that substantial forms, a race of harmless beings, which had lasted for many years, and afforded a comfortable subsistence to many poor philosophers, should now be hunted down like so many wolves without a possibility of retreat. He considered that it had gone much harder with them than with essences, which had retired from the schools into the apothecaries' shops, where some of them had been advanced to the degree of quintessences. We must now say a few words on the technical terms which others of the Greek philosophical sects introduced. Two technical forms of the Platonists, the other sects of the Greek philosophy, as well as the Aristotelians, invented and adopted technical terms, and thus gave fixity to their tenets and consistency to their traditionary systems. Of these I will mention a few. A technical expression of a contemporary school has acquired perhaps greater celebrity than any of the terms of Aristotle. I mean the ideas of Plato. The account which Aristotle gives of the origin of these will serve to explain their nature. Plato, says he, who, in his youth, was in habits of communication first with Cratylus and the Heraclitean opinions, which represent all the objects of sense as being in a perpetual flux, so that concerning these no science, nor certain, 76, knowledge can exist, entertained the same opinions at a later period also. When afterwards Socrates treated of moral subjects and gave no attention to physics, but in the subjects which he did discuss, arrived at universal truths, and before any man turned his thoughts to definitions, Plato adopted similar doctrines on this subject also, and construed them in this way that these truths and definitions must be applicable to something else, and not to sensible things. For it was impossible, he conceived, that there should be a general common definition of any sensible object, since such were always in a state of change. The things, then, which were the subjects of universal truths he called ideas, and held that objects of sense had their names according to ideas and after them, so that things participated in that idea which had the same name as was applied to them. Note 37:1, Arist, Metaph, I6. The same account is repeated and the subject discussed Metaph, Roman 12, 4. In agreement with this, we find the opinions suggested in the Parmenides of Plato, the dialogue which is considered by many to contain the most decided exposition of the doctrine of ideas. In this dialogue, Parmenides is made to say to Socrates, "Then a young man, O Socrates, philosophy has not yet claimed you for her own, as in my judgment she will claim you, and you will not dishonor her. As yet, like a young man as you are, you look to the opinions of men. But tell me this, it appears to you, as you say, that there are certain kinds or ideas, epsilon letter 1F30, delta letter 1F74, of which things partake and receive applications according to that of which they partake. Thus those things which partake of likeness are called like, those things which partake of greatness are called great, those things which partake of beauty and justice are called beautiful and just." To this Socrates assents. And in another part of the dialogue, he shows that these ideas are not included in our common knowledge, from whence he infers that they are objects of the divine mind. In the Phaedo the same opinion is maintained, and is summed up in this way, by a reporter of the last conversation of Socrates, epsilon letter 1F36, nu alpha iota tau iota, letter 1F15 cap alpha sigma tau omicron u, tau letter 1FF6 nu epsilon letter 1F30, delta letter 1FF6 nu. Kappa alpha letter 1F76, tau omicron epsilon tau omega nu tau, letter 1F04 lambda lambda alpha, mu epsilon tau alpha lambda alpha mu beta alpha nu omicron nu tau alpha, alpha letter 1F50, tau letter 1FF6, nu tau omicron epsilon tau omega nu tau, letter 1F74, nu letter 1F10 pi omega nu epsilon mu iota alpha nu, letter 1F34 sigma chi epsilon iota nu. That each kind has an existence, and that other things partake of these kinds, and are called according to the kind of which they partake. The inference drawn from this view was, that in order to obtain true and certain knowledge, men must elevate themselves as much as possible to these ideas of the qualities which they have to consider. 77, and as things were thus called after the ideas had a priority and preeminence assigned them. The idea of good, beautiful, and wise was the first good, the first beautiful, the first wise. This dignity and distinction were ultimately carried to a large extent. Those ideas were described as eternal and self-subsisting, forming an intelligible world, full of the models or archetypes of created things. But it is not to our purpose here to consider the Platonic ideas in their theological bearings. In physics, they were applied in the same form as in morals. The primum calidum, primum frigidum were those ideas of fundamental principles by participation of which all things were hot or cold. This school did not much employ itself in the development of its principles as applied to physical inquiries, but we are not without examples of such speculations. Plutarch's treatise pi epsilon rho letter 1 f76, tau omicron letter 1 fe6, pi rho omega tau omicron upsilon, psi upsilon chi rho omicron letter 1 fe6. On the first cold, may be cited as one. It is in reality a discussion of a question which has been agitated in modern times also, whether cold be a positive quality or a mere privation. Is there, O Favorinus, he begins, a first power and essence of the cold, as fire is of the hot, by a certain presence and participation of which all other things are cold, or is rather coldness a privation of heat, as darkness is of light, and rest of motion? Three technical forms of the Pythagoreans, the numbers of the Pythagoreans, when propounded as the explanation of physical phenomena, as they were, are still more obscure than the ideas of the Platonists. There were, indeed, considerable resemblances in the way in which these two kinds of notions were spoken of. Plato called his ideas unities, monads, and as, according to him, ideas, so, according to the Pythagoreans, numbers, were the causes of things being what they are. But there was this difference, that things shared the nature of the Platonic ideas by participation, while they shared the nature of Pythagorean numbers by imitation. Moreover, the Pythagoreans followed their notion out into much greater development than any other school, investing particular numbers with extraordinary attributes and applying them by very strange and forced analogies. Thus, the number 4, to which they gave the name of tetractes, was held to be the most perfect number and was conceived to correspond to the human soul in some way which appears to be very imperfectly understood by the commentators of this philosophy. 78. It has been observed by a distinguished modern scholar that the place which Pythagoras ascribed to his numbers is intelligible only by supposing that he confounded, first a numerical unit with a geometrical point, and then this with a material atom. But this criticism appears to place systems of physical philosophy under requisitions too severe. If all the essential properties and attributes of things were fully represented by the relations of number, the philosophy which supplied such an explanation of the universe might well be excused from explaining also that existence of objects, which is distinct from the existence of all their qualities and properties. The Pythagorean love of numerical speculations might have been combined with the doctrine of atoms, and the combination might have led to results well worth notice. But so far as we are aware, no such combination was attempted in the ancient schools of philosophy. And perhaps we of the present day are only just beginning to perceive, through the disclosures of chemistry and crystallography, the importance of such a line of inquiry. Technical forms of the atomists and others the atomic doctrine, of which we have just spoken, was one of the most definite of the physical doctrines of the ancients, and was applied with most perseverance and knowledge to the explanation of phenomena. Though therefore it led to no success of any consequence in ancient times, it served to transmit, through a long series of ages, a habit of really physical inquiry, and on this account has been thought worthy of an historical disquisition by Bacon. Note 42:1, Parmenides et Telesi et Principiu Democriti Philosophia, and c. Works, Volume Roman 9, 317. The technical term, atom, marks sufficiently the nature of the opinion. According to this theory, the world consists of a collection of simple particles of one kind of matter and of indivisible smallness, as the name indicates, and by the various configurations and motions of these particles, all kinds of matter and all material phenomena are produced. To this, the atomic doctrine of Leucippus and Democritus was opposed the homomeria of Anaxagoras. That is, the opinion that material things consist of particles which are homogeneous in each kind of body, but various in different kinds. Thus, for example, since by food the flesh and blood and bones of man increase, the author of this doctrine held that there are in food particles of flesh and blood, 79, and bone. As the former tenet points to the corpuscular theories of modern times, so the latter may be considered as a dim glimpse of the idea of chemical analysis. The Stoics also, who were, especially at a later period, inclined to materialist views, had their technical modes of speaking on such subjects. They asserted that matter contained in itself tendencies or dispositions to certain forms, which dispositions they called lambda omicron gamma omicron iota asterisk sigma, pi epsilon rho mu alpha tau iota kappa omicron letter 1f76, seminal proportions or seminal reasons. Whatever of sound view or right direction there might be in the notions which suggested these and other technical expressions, was, in all the schools of philosophy, so far as physics was concerned, quenched and overlaid by the predominance of trifling and barren speculations, and by the love of subtilizing and commenting upon the works of earlier writers, instead of attempting to interpret the book of nature. Hence these technical terms served to give fixity and permanence to the traditional dogmas of the sect, but led to no progress of knowledge. The advances which were made in physical science proceeded, not from these schools of philosophy, if we accept, perhaps, the obligations of the science of harmonics to the Pythagoreans, but from reasoners who followed an independent path. The sequel of the ambitious hopes, the vast schemes, the confident undertakings of the philosophers of ancient Greece was an entire failure in the physical knowledge of which it is our business to trace the history. Yet we are not, on that account, to think slightingly of these early speculators. They were men of extraordinary acuteness, invention, and range of thought, and above all, they had the merit of first completely unfolding the speculative faculty of, starting in that keen and vigorous chase of knowledge, out of which all the subsequent culture and improvement of man's intellectual stores have arisen. The sages of early Greece form the heroic age of science. Like the first navigators in their own mythology, they boldly ventured their untried bark in a distant and arduous voyage, urged on by the hopes of a supernatural success. And though they missed the imaginary golden prize which they sought, they unlocked the gates of distant regions, and opened the seas to the keels of the thousands of adventurers, who, in succeeding times, sailed to and fro, to the indefinite increase of the mental treasures of mankind. But inasmuch as their attempts, in one sense, and at first failed, we must proceed to offer some account of this failure, and of its nature and causes. 80. Chapter 3.